Solving trig equations. In section 6.1, we determined the height of a rider on the London Eye Fair's wheel could be determined by the equation h of t equals negative 65 cosine of pi divided by 15t plus 70. If we wanted to know length of time during which the rider is more than 100 meters above ground, we would need to solve equations involving trig functions. Solving using known values. In the last chapter, we learned sine and cosine values at commonly encountered angles. We can use these to solve sine and cosine equations involving these common angles. Example 1. Solve sine of t equals half for all possible values of t. Notice this is asking us to identify all angles t that have a sine value of half. While evaluating a function always produces one result, solving for an input could yield multiple solutions. Two solutions should immediately jump to mind from the last chapter. T equals pi divided by 6 and t equals 5 pi divided by 6 because they are the common angles on the unit circle with a sine of half. Looking at a graph confirms that there are more than these two solutions. While 8 are seen on this graph, there are an infinite number of solutions. Remember that any coterminal angle will also have the same sine value, so any angle coterminal with these our first two solutions is also a solution. Coterminal angles can be found by adding full rotations of 2 pi, so we can write the full set of solutions. T equals pi divided by 6 plus 2 pi k, where k is an integer, and t equals 5 pi divided by 6 plus 2 pi k, where k is an integer. Example 2. A circle of radius 5 multiplied by square root of 2 intersects the line x equals negative 5 at 2 points. Find the angles theta on the interval 0 less than or equal to theta less than 2 pi, where the circle and line intersect. The x-coordinate of a point on a circle can be found as x equals r cosine of theta. So the x-coordinate of points on the circle would be x equals 5 multiplied by the square root of 2 cosine of theta. To find where the line x equals negative 5 intersects the circle, we can solve for where the x value on the circle would be negative 5. Negative 5 equals 5 multiplied by the square root of 2 cosine of theta, isolating the cosine. Negative 1 divided by square root of 2 equals cosine of theta. Recall that negative 1 divided by square root of 2 equals negative square root of 2 divided by 2, so we are solving cosine of theta equals negative square root of 2 divided by 2. We can recognize this as one of our special cosine values from our unit circle, and it corresponds with angles theta equals 3 pi divided by 4 and theta equals 5 pi divided by 4. Example 3. The depth of water at a dock rises and falls with the tide. Following the equation, f of t equals 4 sine of pi divided by 12t plus 7, where t is measured in hours after midnight. A boat requires a depth of 9 feet to tie up at the dock. Between what times will the depth be 9 feet? To find when the depth is 9 feet, we need to solve f of t equals 9. 4 sine of pi divided by 12t plus 7 equals 9. Isolating the sine, 4 sine of pi divided by 12t equals 2. Dividing by 4, sine of pi divided by 12t equals half. We know sine of theta equals half when theta equals pi divided by 6 or theta equals 5 pi divided by 6. While we know what angles have a sine value of half, because of the horizontal stretch compression, it is less clear how to proceed. To deal with this, we can make a substitution defining a new temporary variable u to be u equals pi divided by 12t. So our equation sine of pi divided by 12t equals half becomes sine of u equals half. From earlier, we saw the solutions to this equation were u equals pi divided by 6 plus 2 pi k, where k is an integer, and u equals 5 pi divided by 6 plus 2 pi k, where k is an integer. To undo our substitution, we replace the u in the solutions with u equals pi divided by 12t and solve for t. Pi divided by 12t equals pi divided by 6 plus 2 pi k, where k is an integer, and pi divided by 12t equals 5 pi divided by 6 plus 2 pi k, where k is an integer. Dividing by pi divided by 12, we obtain solutions. T equals 2 plus 24k, where k is an integer, and t equals 10 plus 24k, where k is an integer. The depth will be 9 feet, and the boat will be able to approach the dock between 2 a.m. and 10 a.m. Notice how in both scenarios, the 24k shows how every 24 hours the cycle will be repeated. In the previous example, looking back at the original simplified equation, sine of pi divided by 12t equals half, we can use the ratio of the normal period to stretch factor to find the period. 2 pi divided by 12 equals 2 pi multiplied by 12 divided by pi equals 24. Notice that the sine function has a period of 24, which is reflected in the solutions. There were 2 unique solutions on one full cycle of the sine function, and additional solutions were found by adding multiples of a full period. Solving using the inverse trig functions. Not all equations involve the special values of the trig functions we have learned. To find the solutions to these equations, we need to use inverse trig functions. Example 4. Use the inverse sine function to find one solution to sine of theta equals 0.8. Since this is not a known unit circle value, calculating the inverse theta equals sine inverse of 0.8. This requires a calculator, and we must approximate a value for this angle. If your calculator is in degree mode, your calculator will give you an angle in degrees as the output. If your calculator is in radian mode, your calculator will give you an angle in radians. In radians, theta equals sine inverse of 0.8 is approximately 0.927, or in degrees, theta equals sine inverse of 0.8 is approximately 53.130 degrees. If you are working with a composed trig function and you are not solving for an angle, you will want to ensure that you are working in radians. In calculus, we will almost always want to work with radians since they are unitless. Notice that the inverse trig functions do exactly what you would expect of any function. For each input, they give exactly one output. While this is necessary for these to be a function, it means that to find all the solutions to an equation, like sine of theta equals 0.8, we need to do more than just evaluate the inverse function. To find additional solutions, it is good to remember 4 things. The sine is the y value of a point on the unit circle. The cosine is the x value of a point on the unit circle. The tangent is the slope of a line at a given angle. Other angles with the same sine, cosine, tangent will have the same reference angle. Example 5. Find all solutions to sine of theta equals 0.8. We would expect 2 unique angles on one cycle to have this sine value. In the previous example, we found one solution to be theta equals sine inverse of 0.8, which is approximately 0.927. To find the other, we need to answer the question, what other angle has the same sine value as an angle of 0.927? We could think of this as finding all the angles where the y value on the unit circle is 0.8. Drawing a picture of the circle helps show the symmetry. On a unit circle, we would recognize that the second angle would have the same reference angle and reside in the second quadrant. The second angle would be located at theta equals pi minus sine inverse of 0.8, or approximately theta approximately pi minus 0.927 equals 2.214. To find more solutions, we recall that angles coterminal with these two would have the same sine value, so we can add full cycles of 2 pi. Theta equals sine inverse of 0.8 plus 2 pi k, and theta equals pi minus sine inverse of 0.8 plus 2 pi k, where k is an integer, or approximately theta equals 0.927 plus 2 pi k, and theta equals 2.214 plus 2 pi k, where k is an integer.